Okay, I think it's about time. Good morning. Welcome. Thank you for being here. Before starting, I'd like to say that you can ask your questions in Slido, sly.do. You can go to the Build Stuff LT room, and for this Zeta room, make your questions there. So, does it work? Yes. Check. It doesn't. So, my name is Pedro. I'm a software engineer. I've been working for the last 10 years mostly on backend systems, mainly HTTP-based backend systems, both in .NET and the JVM. I'm also a teacher at the Lisbon Polytechnical Institute, where I teach concurrent programming courses and also web application development. And as I've said, I've been working mainly in backend, using HTTP-based systems in .NET, and mostly asynchronous implementations. With .NET, I've worked with the several asynchronous models that they have until stabilizing in the newest or the newer async await. In the JVM, I have been working mostly with RX Java and reactive streams. Kotlin. Kotlin is a static typed language created by JetBrains around 2011. It has an excellent JVM integration. It does not target only the JVM. It also targets native in JavaScript, but it's more popular in the JVM. And it has a very good integration with all the JVM ecosystem. So it's rather easy to have a project where I'm using Java and Kotlin side by side without major issues. The popularity increased significantly in 2017 because it was started to be considered an Android official language, so it's supported by Google. Almost half of the documentation that Google produces for Android includes Kotlin. On the server side, it is also increasing their popularity, namely Spring Boot 2.0 already supports Kotlin, so it's rather easy to create Spring-based projects using Kotlin. The latest version was released in October 2018, version 1.3, and it was the first version where coroutines are now a stable feature. Until now, they were rather experimental. The API was changing. Now, the core API for coroutines is stable and is fully supported in production. So I think it's one of the features of the language that will start being used more and more after the 1.3 release. So, first, why asynchronous? Well, in the type of systems where I work, backend systems, most of the times the systems are waiting for other things to happen. I'm contacting external services, namely if we are using microservices. For a service to perform its work, may have to contact another external or more than one external services or more than one data store. So we end up waiting and waiting for other things to happen. And when these waits are blocking, they are monopolizing a thread. They are fully occupying a thread. And both in the JVM and in .NET, threads are very costly. They are costly to create, but also they are costly to operate because they take a lot of memory. For instance, a JVM by default, a Java thread will occupy 1 megabyte of memory just for the stack. More than that, there are some threads which are not only costly, they are special. For instance, when we are on client-side development, there is a very special thread called the UI thread. And if I block the UI thread, the system becomes unresponsive. And in certain cases, the platform forbids me of doing certain type of blocking operations on the UI thread. And for me to do any kind of I/O, it is not necessary to block a thread. Most operating systems, Linux, Android, Windows, already support asynchronous I/O natively in the operating system stack. So it is possible to do I/O operations, to talk with an external service, to talk with an external database without blocking any thread. It's not a matter of making the work being done by a different thread is not blocking any thread. None, really. And that is rather important. For instance, take an example that is rather common in the systems where I work. I have a service that receives incoming requests, and during the processing of that incoming request needs to perform an outgoing request to an external service. And if I have a throughput of 500 RPSs, 500 requests per second, and I'm using an external service with a latency of 2 seconds, I will end up with 1,000 threads blocked on that outbound I/O. So on any given moment in time, I will have 1,000 threads just there, parked, waiting for the external I/O to complete. You may say, okay, 2 seconds is a rather high latency. But if for some reason the external dependency has normally a smaller latency, but it increases the latency slightly, I start to have more and more and more threads blocked on the I/O, and the typical consequence is that I ran out of threads to process new incoming requests. Using asynchronous I/O, I can have a different setting. So the inbound request comes in, I start processing it on the blue thread, I start an outbound I/O, and the blue thread is immediately returned to the HTTP server stack. And there is no thread waiting on the external I/O. Finally, when the external I/O completes, there will be a thread from the external I/O thread pool, the green thread, and the remaining of the request will be processed on the green thread. Between the blue and the green, there will be no blocked thread. So I can have 500 RPSs, I can have 1,000 pending requests without having 1,000 pending threads. Typically, we operate with in asynchronous models, we operate with very small thread pools. Typically as much as the CPU cores. So very low memory required for the threads, very low thread switching because I have a very small amount of threads, even if I have a huge amount of pending requests being processed. Some notes. Asynchronous is not the same as parallel programming. I can have an asynchronous flow that is sequential. So I'm not necessarily trying to explore parallelism. I'm trying to explore asynchronism, which is rather different. Also, it's not the same as a synchronous communication pattern. So I may be implementing a synchronous communication pattern, a request-response pattern using HTTP, but the implementation internally is fully asynchronous. Okay? And it will not make single things faster. So a single request using asynchronous I/O, because asynchronous I/O is slightly more complex, may be a little bit slower. Typically something that doesn't matter because most of the time we are waiting for the external system to respond. So if the external system takes 5 milliseconds, waiting some more microseconds because the synchronous I/O is slower is not a big deal. What we are trying to achieve first is more throughput, better responsiveness, namely in client-side systems, because I'm not blocking the UI thread. Overall, I'm trying to achieve a better resource usage, a better thread usage when using asynchronous I/O and asynchronous API. On the JVM, there are lots of asynchronous APIs. We have callbacks, for instance, new IO2 that appear on JDK7, the Apache HTTP client, all they use callbacks. They use an asynchronous model based on callbacks. We also have APIs based on features, for instance, the Sync HTTP client, the new JDK11's HTTP client support features, and we also have reactive streams and RX Java. For instance, the new Spring Web Flux supports reactive streams. And these are different models of dealing with asynchronism in our code. However, things are not so simple. So let's consider an example that we will use throughout the presentation. I have a simple function with a loop, with a blocking operation in the middle, and a function that does something with the result of the blocking operation. And I have a loop carried dependency through that accumulator, meaning that this code is sequential. I'm not trying to parallelize this code. I'm trying to avoid having a blocker thread in that blocking operation. So I can try to use a callback. So assuming that I have, instead of a blocking operation, I have an async operation with callback, I could try to use the callback. The problem is that the result will be available on the callback, and I want the result to be used on the do something with. So I have the value on one place, but I need to use it on another place. So typically, I need to bring the do something inside the callback, which breaks the flow. So that do something with is no longer inside the for, so I need to do callbacks inside of callbacks inside the callbacks, and I easily reach what is known as callback hell. Because this normal flow, I have a simple loop, and I'm iterating through the loop, breaks when I start to use callbacks. I can try to use futures, so assuming that I have an async operation that returns a future, I could try to use a future and then do a future.get. But the future.get is blocking. So I'm not blocking in the first line, I'm blocking in the second line. It's almost the same thing. But modern futures, for instance, completable future, also supports combination functions such as the then except. But they are very similar to callback. So that means that I have to move the do something inside the callback, meaning that I break the flow, meaning that I can no longer use a simple for, I need to use recursion or something like that. The end conclusion is that callbacks, futures, observables, reactive streams do not fit well into the structure of imperative code, where functions are created by sequence of statements, and I have ifs and fors and try and catch. Futures and reactive streams, they fit very well into a functional style, and they impose a functional style. That's nothing wrong with it. The problem is that by using asynchronicity, typically I need to change the style that I use in my code, which is not necessarily a good thing. I may prefer functional style, but I would not like to be imposed into a functional style just because I'm using asynchronicity. And for instance, currently I work on a code base that uses a lot of Rx Java, and sometimes when I want to look at the code and try to find out or try to understand some part of business logic, I go into that business logic, and what I typically find is flat maps everywhere. And if everyone worked with Rx Java know what a flat map is. So I'm trying to figure out the business logic behind that code, and it's callbacks, flat maps, maps, zips. So all the synchronicity machinery is inside my business code. So the challenge is, how can I create code that doesn't block threads while still using the same classical imperative synchronous coding style that we learned at school and that we are familiar with? Well, most of the languages, C#, JavaScript, Python, Dart, are using the async await solution for that. So my first expectation when I start studying Kotlin was that, okay, they are going to support also the async await. And it's going to be similar to C# and JavaScript. So if Kotlin had async await, which doesn't, but if it had, it would be something like that. I would have this normal code, I will have the function that returns a feature, and I will add a special await, the magic await, and that magic await transforms a future of t into a t, without blocking the hosting thread. And that's it. So I use a future, I put that special operator, await, and everything is done. Well, not exactly everything, because When using async await, I need to change the signature of my function. So even if I return an int, the signature of the function needs to be a completable future of int, or a future of int. If you are using C#, it needs to be a task of int. So I work as if working directly with ints, spreading awaits in my code, but the function returns a future of int. Meaning that the function that we'll call this function also needs to deal with this. And we used to call that asynchronous is viral, because when I start using asynchronous in one place, it will spread all over the code. However, Kotlin decided to use a slightly different strategy. They decided to use coroutines. And if you go to Wikipedia, coroutines say that a coroutine is a generalization of a subroutine that allows multiple entering points for suspending and resuming execution. So I can suspend and I can resume execution in the middle of the regular imperative flow. And it's a rather old concept. The first published reference to coroutines is from 1963, where Conway stated that coroutines greatly simplify the conception of a program that do not communicate with each other synchronously. So it's not a new concept. I think it's a new concept in the more mainstream languages. So let's start with coroutines and all the concepts that live around coroutines in Kotlin. There are four main concepts. The first one is the concept of suspend function. So let's consider again our example, synchronous example, that returns a future, and then I only need to do this. So I need to add a special modifier to the function, and the function is now a suspend function. A suspend function can have its execution suspended in the middle of the flow. And what was the await operator that exists in C#, for instance, is now an extension function called await. So there is still an await, but the await is not provided by the language, it's provided by a library. Okay? That is important because this await is not tied to a special type of feature. In C# or in JavaScript, there is only one type of feature. JavaScript will be promises, C# will be task of T. In JVM, there are lots of libraries, each shown with its specific type of feature. On JDK8, we have completable feature. When using Guava, we have listenable feature. If you are using, for instance, Akka, there is a feature specific to Akka. So having something that is library provided and not the language provided, it's also important. It's important. So await is an extension function and not a language operator. If we are using IntelliJ, IntelliJ will have that icon over there saying that beware, on this line there will be a suspension. It's a suspension point. And most importantly, the return type is an int and not a future of int. So I don't have to propagate futures on futures on futures. I have a function that returns the future because it's a legacy library that I'm using. I put an await, and afterwards I don't have to deal with futures anymore. It's normal code. The only thing that is different is that I need to add that suspend modifier on the function. If, for instance, I have a caller 1 that calls example, I just call it directly. I don't need to use any await there. Okay. Yesterday I was seeing Jimmy Bogart's presentation, and I was seeing all those awaits in the asynchronous code, which is much, much better than using callbacks. But since I'm now using more and more Kotlin, those awaits seemed strange to me. Well, why so many awaits in the code? Here, I need to do a await when I'm interfacing with legacy code that does not use coroutines. when I bring that code inside coroutines, I don't use await anymore. So just regular code. If I have a caller2 that calls caller1, that calls example, I don't have to use any await. There is a slight catch here, but I will talk about afterwards. So I have a future-like object, completable future, listenable future, whatever future. I need to convert it into coroutines using typically a library provider await extension function, and then I have suspend functions that work with these and not with future of these. Okay. If we look inside the await, we will find a very special function, and I think it's the most important thing to understand when studying coroutines and when working with coroutines, which is that suspend coroutine. That suspend coroutine, it's a little bit odd at first sight. What it does when I call it, so I have a future, and I call the suspend coroutine, and I pass a lambda. That lambda receives a continuation and is executed immediately. So when I execute suspend coroutine, inside suspend coroutine, that lambda will be executed. So the future then accept will be executed immediately. And that lambda receives a continuation. Okay. What is this continuation? This continuation is the callback that I call to resume the flow. So what I do is future then accept, for instance, and a couple of milliseconds afterwards, when finally the future completes, that code in green will call continuation.resume. And this is where the magic, well, it's not magic, it's code, happens. The call to resume will re-enter the suspend coroutine and will continue. So I called the suspend coroutine in the slightly yellow thread, and I end the suspend coroutine in the different thread. So there was a suspension point, there was a resume, potentially in a different thread, but the flow seems to be completely sequential. Okay. Well, if I look into that code, it seems a little bit odd, a lot of curly braces. It's typical in Kotlin. But I can easily hide that suspend coroutine into an extension function because Kotlin supports extension functions. In this case, an extension function on completable future, and that's it. What I have to, or the only thing that I have to use is the await, nothing more. So if you are using your own future, or if you are using your own callback-based API, you can easily convert that into coroutines by using the suspend coroutine function. That example there, it's a little bit more complex. In the previous example, I did not handle errors. In this case, I'm already handling errors. So I have a continuation.resume or continuation.resume with exception. To handle cancellation, that await is slightly more complex. But it's something that I hide into an await function, and then I use the await function. So suspend coroutine function provides continuation to resume execution, seems to start in one thread and end on the other, creates a suspension point using any callback-based API, so I'm not tied to a particular type of feature. And typically, it is used inside await extension points. The only problem is that I can only use suspend coroutine inside suspend functions. Okay. A suspend function, they compose directly. So when I'm in a suspend function, I can call a suspend function directly. I don't have to deal with futures anymore. And this is possible because the compiler transforms the suspend function into a state machine. This is very similar to what the C# compiler does or the JavaScript runtime does when using async await. They transform a sequential flow using ifs and whiles and tries and catch into a state machine. It is that transformation into a state machine that allows different segments of this flow to be executed in different threads. But the Kotlin compiler also does something that is not done by the C# compiler, which is it changes the signature of the function. And the function starts to use one thing which is called continuation passing style. And on a continuation passing style, when I call a function, I need to also pass the continuation. This is completely hidden from us. If we go to the bytecode, it will be there. I will see that the signature is different. But when using the Kotlin compiler, this conversion is hidden for us. However, there is a major implication, which is I cannot call a suspend function directly from a non-suspend function. So if I have a non-suspend caller, and if I try, which is not suspend, if I try to call caller2, I will receive this famous error. Suspend function should be called only from a coroutine or another suspend function. And this brings us to the second important concept of coroutines, which is coroutine builders. So, what I have here is, I have, for instance, legacy I/O, legacy asynchronous I/O. I still use my library of choice to do asynchronous I/O. I use await or suspend coroutine to convert them into coroutines, so I'm in the orange blocks. Then I'm dealing not with futures anymore or callbacks anymore, I'm dealing with these. But if I need to call this from a regular function, I cannot do it directly. Also, suspend is part of the function signature. So I cannot override a non-suspend method with a suspend method. For instance, currently, Spring MVC does not support that I define, that I use a suspend function in a controller. So how can I deal with this? With one thing called coroutine builders. The coroutine builder is the thing that allows me to do the reverse interface, to go from regular functions into suspend functions. And what a coroutine builder does is that it receives a suspend function and returns a future-like object. Because Kotlin tries to target different environments, it does not use a completable future. It has its own future, yet another one, which is called deferred of t. And in the case where the coroutine does not produce any result, it just produces some side effect, something similar to task in C#, it's called job. But I also have coroutine builders that produce a completable future, and I have a special one that is blocked, typically only used for tests. So what I have is, on the edges, I have regular functions that eventually return futures. So in the outbound edge, I'm still using a normal library. In the inbound edge, I'm still using a normal library, Vertex, Spring, whatever. The core will use coroutines. I need to do special adaptation at the edges, but the core will be straightforward code. This also helps us understand what is the difference between, why we call it coroutines, but the modifier is suspend. So what is the difference between a suspend and a coroutine? Well, suspend is the way that I define coroutines. So a and the suspend function will be compiled into a state machine. A coroutine is an instance of that state machine. Okay? Suspend function defines state machine. Coroutine is an instance spinning of that state machine. So let's start with the Spring controller. So I have a very simple handler with an attribute or an annotation. I get example, I have some logging information, and I called example. If I try to compile this, it will say suspend function should be called only from a coroutine or another suspend function. So what I need to do is this. First, Spring already supports asynchronous handlers. They support asynchronous handlers using both completable feature or a special kind of Spring, which is deferred result. So I will use deferred result. And then I will do a launch. That launch is a builder. And inside the launch, I can have a suspend function. So that launch will create the coroutine. The coroutine will start working. And as a side effect of the conclusion of the coroutine, I will set the result of the deferred result. So in these two lines below, if I have success, I will set the result with the result of example 7. Otherwise, I will set the exception result. Okay, and that's it. I have to do a launch, and then inside the launch, I can use suspend. Again, I have a sync IO on one edge, I have the await, I have the suspend in the middle. On the other edge, I have a Spring handler, and I use a coroutine to adapt between those. And if I run it, I can see that the controller handler started and ended immediately on that HTTP NIO thread, which is a thread from the server. In this case, I'm using Tomcat. So the thread from the server is immediately released, and it will be available to handle a new request. And I can see that afterwards, it finally completes in the different thread, in this case, default dispatcher worker 1. Okay. So Spring calls the handler, receives a deferred, and only when the deferred is completed is the response returned to the client that called me. However, if I look into this code, it's still rather complex. So basically, I want to do an handler that calls example, and I have all this gray code that is boilerplate code. So can we do better than this? Yes, we can. It's very easy to encapsulate that code inside an async handler. For instance, I have an async handler function. That async handler function receives a block. Notice that the signature of the block function contains the suspend. Suspend belongs. It's not an implementation detail. It's something that appears in the function signature that calls the block and sets the result and sets the error result. And the usage is just something as simple as get the example equals async handler, something that we can do in Kotlin. Kotlin is a lovely language. And then I just call example 7. So the end result of creating an asynchronous handler in Spring is just that. The only thing that I need to add is that it appears to be a decorator async handler. And that's it. Okay, third important concept, coroutine context. What is a coroutine context? Coroutine context is a set of immutable elements which have a purpose which is similar to thread local storage. Okay? When working on server side, it is rather common to have lots of ambient information. For instance, in Spring, the local transaction is stored in the current thread. That works well when I have a single thread for all the requests. But if the request is switching between threads, I cannot use local thread storage. So coroutines have a similar context, a similar concept, which is coroutine context. That is all the information that I might need during the execution of the coroutine. For instance, to store the current transaction. It is available during the entire coroutine lifetime via the coroutine context. I can call coroutine context wherever I want, and I will access the coroutine context. It is immutable, so it's not exactly the same as thread local storage. I cannot change it, which is good. It is defined when I build the coroutine, and I can change it by creating a completely new context using uContext. Also, those elements can also be used to change behavior of the coroutine. And one of the important behaviors that I can change is the thread dispatching. What is the thread dispatching? So, on coroutines, I'm using continuations to register callbacks. And those callbacks will be called in threads that belong typically to the library that I'm using. For instance, if I'm using a synchronous client, the asynchronous HTTP clients from Apache, it will have its own thread pool, and the callback will be called in its own thread pool. But I may want to continue the execution in a different thread. For instance, if I'm working with Android, and upon receiving a response, I need to change the UI, I cannot change the UI in an I/O thread. I need to change the UI in the UI thread. So I need to continue not in the same thread where the callback happened. I need to continue in a different thread. This is done using thread dispatchers. And by default, or out of the box, there is already 3 dispatchers that are available in these static properties. Default one, that is used by default. I/O, when I need to use blocking I/O. And main, when I need to defer or to dispatch into the main thread. What is the main thread? It depends. If I'm on Android, it's the Android UI thread. If I'm on a Swing project, it is the Swing's UI thread. So that concept of the main thread may depend on the hosting environment. As I've said, there is also an experimental dispatcher which is unconfined. It is very interesting. The unconfined is do not change the thread. So execute the remaining of the coroutine in the thread that called the callback, which typically is a thread that comes from another place. As I've said, I can define the context and the dispatchers when creating the coroutine, for instance, in a launch, or I can change using with context. For instance, I have here a small example. In the top part, I have created a new dispatcher using a single thread, using an executor from Java. And I called that thread the example thread. And then inside the Spring handler, I did with context example dispatcher. And if I look into the logs, I will see that all this code is being run by the example thread. Okay? So, for instance, if I want everything to be run in my thread pool or to be run in a single thread that I completely control, I create a dispatcher and I use, for instance, with context to force that dispatcher. By the way, in any place in a coroutine, I can use coroutine context and then use the index operator to access an element. So if I add things into the context, for instance, the identity of the caller or the current transaction, I can then retrieve that information using the indexer operator. And finally, the fourth concept, which is the concept of Coroutine Scope, which is a rather new. This was introduced only in version 1.3, and the first time that it was made public it was around September, I believe, or perhaps a little bit before. So it's a rather new concept, but it's already a stable concept. It is in 1.3, and it is fully supported. And what does it try to solve? Consider this example, where I have the same handler, but I reduce the timeout for Spring. So I have a function that takes a couple of seconds, but the timeout that I defined on my web stack is just 1 second, meaning that the request, the incoming request, will time out and will immediately produce a 503. And if I look into the logs, I will see that roughly around 1 second, I have the Spring framework telling me, okay, there was a request timeout. I am sending a 503. But a couple of seconds after, I still see the coroutine doing things. Because I launch a coroutine, the coroutine starts doing things in that 4. The request that launched the coroutine ends, but the coroutine still works, which is something that I don't want. If you were on Jeff Richter's keynote yesterday, he stated that cancellation is a very important subject in cloud. And it stated that the signature of the functions in C# and the usage of the token, of the cancellation token should be different. This is exactly the same problem. I need to deal with cancellation. And the way that cancellation is defined in Kotlin is very interesting. Namely, it doesn't suffer from the issue that Jeffrey stated yesterday. So after 1 second, the request timeout, a 503 response is automatically produced, but the coroutine still keeps spinning. This raises the issue of life cycle management, because a function can create 1 or more coroutines. And these coroutines internally can create more coroutines. That's why the coroutines need to be created inside the scope. The scope is the thing that we have to aggregate a set of coroutines. I didn't mention it, but if you looked into the launch, let's try to go into here, you will see that the launch was done on a global scope, which is a bad idea, because the global scope will only end when the application ends. And I want that coroutine to end when the incoming request ends. So global scope is not a good idea to have. Before defining how I can handle this, scopes are used also to create parent-child relation between the coroutines. And these parent-child relations are very important. For instance, a parent coroutine only completes when all the childs complete. So there are no leaked childs running after the parent completes. Also, if the parent cancellates, it propagates the cancellation automatically without any need for explicit cancellation tokens, as with C#, through all the children. If a children throws an exception, that exception will propagate to the parent. So what I need to do here is create a new scope. What I use as a scope depends on the context. For instance, the majority of the examples that you see in the documentation are for front-end development. And in that case, the scope is the activity. If you are familiar with Android development, the activity defines the screen. And if the user goes out of the screen, the activity ends. And I want everything that was related with that activity to end. So it makes sense for the scope to be the activity. In this case, the scope is a request. And I'm using the deferred result to represent the request. If the request ends, I want everything that was created in the context of the request to be cancelled. So I need to create my own scope, which derives from deferred result and implements a coroutine scope. I will not go into the details. I just need to define an handler. And in that handler, on timeout, that on timeout is automatically called by Spring. I will cancel. And by cancelling the coroutine, I will cancel any children coroutine that were launched. Okay. So, and if I look into the logs, I can see that the deferred result times out roughly around 1 second, and immediately the job is cancelled and everything ends, and I don't have any further activity. Okay. So any inner coroutine will also be cancelled as long as scope is properly propagated. That means that I cannot use global scope. Anything that I create using global scope will be global, will not be subject to the lifetime of the request or the lifetime of the activity. So, I'm almost ending. An interesting example taken from a presentation on 2007. To highlight the difference between the async await as available on C# and the coroutines as available in Kotlin. For instance, in this example, I load 2 images, and then I do something with those images. And on the left column, I have C#. On the right, I have Kotlin. And if I want to do it sequentially, if I look into Kotlin, I don't see any await. I see straight sequential code. Asynchronous, but sequential. If I look into the C#, I see the awaits, okay? Which are rather odd when I need to do a await and the function does not return anything, and I must not forget to put the await there. If we go into the parallel, we'll see the exactly opposite. On the C#, I call the load image and load image without the await, so that they run in parallel. And then I need to do the await when retrieving the value. In Kotlin, I need to be explicit. I need to use async, which is a coroutine builder, because if I want it to be parallel, I need to create a coroutine, a new coroutine. So in this case, I'm creating 2 different coroutines for the load image, and then I'm awaiting on their result to do do something with. So in Kotlin, concurrency is explicit, and one of the main points of making concurrency explicit is that concurrency is hard. And when you have concurrency, you need to deal with concurrent access to shared memory. And you start needing to use locks and mutexes and synchronization structures. And this is true in C#, this is true in Kotlin. Async await will not solve it. Coroutines will not solve it. So they decided to make concurrency explicit. If you want to have something in parallel with another, you have to be explicit about it. So, 4 core concepts around coroutines: suspend functions, builders, the context, and finally, a more recent concept, but very important one, which is the scope. Some resources. Okay, I've published these examples, just for educational purposes, under my GitHub repo, PMHS Felix, Kotlin/Coroutines. The presentation is not there yet, but it will be available on the speaker deck. I strongly suggest all the videos by Roman Elizarov. Roman Elizarov is one of the designers and responsible for the implementations of coroutines. He has 2 videos on Kotlin Conf 2007 and 1 video on 2018. Strongly recommend. Almost everything that I learned from about coroutines were from these videos. There is also a coroutine guide available in the Kotlin GitHub. And finally, JetBrains is creating a new web application framework, yet another, called CTOR or KTOR, which is completely based on coroutine. So if you want to see a design that is sought out from the beginning based on coroutines, this KTOR, which is beta right now, is a good place to start. And finally, thanks for being here and for your attention. I think I need to go here. Let me see, no, not here, here. To see if there are any questions. So I will start perhaps with the room. Any questions that you would like to make? No questions? I will make some questions. Yes. No, what I've said, I think, was there's a catch where when I'm using suspend, I don't have to put into the signature the future, but the downside is I can only call a suspend from inside another suspend. So as long as I'm in suspend function, let's call suspend function, everything is nice. If I need to have a non-suspend function calling a suspend function, then I need to use a coroutine builder, except if this function is inline. For instance, Kotlin has a lot of inline functions, and inline functions don't do a call. They expand the code inside. For instance, to do high-order functions, such as filters and maps and so on. Most of them are inline. And in that case, I can call a suspend inside a non-suspend because the non-suspend inlines the other, or it's inlined. Yes, because an inline function expands the function in place.
Yeah, I understand the concept of inline, but the other language is just notation or something for compiling.
Yeah, no, disguise is a keyword. It's a keyword that we put in the function signature, yes. Any more questions? Okay, what does suspend function looks from Java? It looks odd because it has a different signature. Okay, because inside the compiler transform that into a state machine that uses the continuation passing style. So typically, if I want to interface from Java, I will not interface directly from Java into suspend. I will interface from Java into a non-suspend function that I write in Kotlin. And in that non-suspend function that I write in Kotlin, I will use a coroutine builder to launch the coroutine and the suspend function inside. Okay. Any more questions? Yes? Exactly. Yes. It's performed via the context. So you don't have to pass anything explicitly. You don't have to pass a cancellation token. So you don't change the signature just because you have cancellations. You can ask via the context, well, there is a isCancelled function that you can use everywhere and ask if the coroutine that I'm currently executing was cancelled or not. More than that, all the suspend functions that are provided by the library throw an exception, when there is a cancellation. Similar to the thread exception that occurs when the thread is interrupted. In this case, for instance, if I'm inside an await, so I'm not looking into the flag because I'm waiting on the await, and the coroutine is cancelled, the await will immediately return with an exception. And then I can decide to ignore the exception, or I can do something with the exception. Meaning that cancellation is always cooperative, but it's easier to do than in C# because it's more fail-safe. I don't have to remember to propagate the cancellation token and have that cancellation token into the signature of all the functions. So does ending a scope automatically invoke all the finalizers within the coroutines? Ending a scope cancels everything. By cancelling everything, if the coroutines were waiting on suspension points, they will immediately get out of that suspension point via an exception. However, if I'm in a legacy blocking I/O operation that does not know nothing about this, it will remain there. And if I have finalizers, it throws the exception and it goes through all the finalizers that I have in the stack. So it's not regular exception handling for that case. At which point inside the suspend function is a cancellation performed? Yeah, in any suspend point. So I can pull, I can ask. So I'm in a for doing something computational intensive, and I can ask, am I cancelled? Am I cancelled? Or if I'm waiting, if I'm using one of the library provided functions, that wait is interrupted by an exception. If I'm creating my own await functions because I'm using my own library, I need to be careful to make them also cancelable by throwing an exception where the coroutine is cancelled. Any more questions? No? Once again, thanks a lot for being here. I hope you liked.